So this is a famous chapter 4.5. Even if it has different number, all Americans around the world, America, I guess? No, everyone in America who take class Calculus 1, they have this chapter. So not in our countries, actually. Now they start putting more applicational problems, but I never heard of any of these. So I had to learn them when I was teaching them. It's very fascinating and very fun. I actually do regret I did not know any of these. So first we're going to write down some boring definitions, and then we're going to jump into applications. Constraint optimization problems are problems for which a function, which is called objective function, OF, I'll be using notation of OF, is to be minimized or maximized, subject to constraints, minimized or maximized, optimized. It's going to be optimized, and that's where the name comes from. So there's lots of English, but I will never ask you about this anyways, but that is a nice explanation. Constraint optimization problem is when you're asked to build a house and you have constraints. Either you don't have infinitely many money, or you don't have infinitely many territory for the house, or both. So you need to make this perfect house, minimize or maximize the price, minimize the price of the house, maximize the volume, blah, 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 whatever you want, with those constraints. So that's the idea. And the model looks like this. We're going to jump into a problem right away, but I always like to mention that there is a model. And the model, so we becoming modelers in Harvard universities for a while already. I think for 7 years, they start doing this crash course for freshman STEM people to do mathematical modeling or just modeling. So physics, math, chemistry, engineering gets together, computer science, data science, and they do modeling. This is a special course. We also have a course called modeling. You will take it later, I think. So model consists of objective function. That's the one we want to optimize, minimize, or maximize. And then constraints. How would you explain what this word constraints means? Constraints. What is that? Constraints. What did you say? Limitations. What else did you say? There are more synonyms. Constraints. What do constraints means? It's a weird English word. Restrictions. That's what I put in my notes. Limitations, restrictions. Very good. Thank you. Not I-E. Restrictions. So your model have objective function. Also the weird word objective function. It's a function and it's an object of our work. That's kind of how I see it. Objective function. We're going to be concentrate on that function to minimize or maximize it. And we're going to have a model, and this is a system, so it's a model. And we have number 1 and number 2 equations, and I'm going to explain you how to build the model so you slowly become a modeler. How are you going to build a house by yourself with the knowledge of STEM? So all of this builds you to the professional modeler. And we have students who are hired and they just got the plan, okay, build the best sink that we should put in the hospital. And I was doing mathematical modeling on this with engineers. Apparently some sinks splash too much, and people who have gonorrhea or all the kind of restroom diseases, they wash hands and it splashes too much, and if the van is too close, it goes to the ventilation system and makes other people sick who were just there with a broken hand, for example, with things. So CDIF is a good example of that case. So we were designing a thing that will not splash in too much. It's a genius idea. It's so simple, just to make better object to prevent disease spread in hospitals. So how can you do it by yourself? Nobody will tell you how, because you're already hired to do that. You claim you know in your CV, and now you're hired and you get 6 digits. Can you do it? So that's our job, is to slowly teach you about that. Well, let's start with fencing problems. Those are my favorite ones because they're the easy ones. And then in your homework, you will have lots of complicated problems. We're giving, with the given fencing materials, a fence. We're trying to build a fence of 2,400 feet long. Build a rectangular fence with maximum area. Find dimensions and the maximum area. So, Uncle Jim asks you to help because you're a STEM student, and help to build a fence in his yard for the horses. Yeah, I like horses. For the horses. So they need a fence. And then Uncle Jim already went to Lowe's and got Costco maybe, and got very good discount on something. So he already has 2,400 feet of material. So you cannot go above that, beyond that. But then it's a question, do you know that the shape matters? This shape is a fencing, nice fence. Here's your horses, here is a horse, and here's the horse, and here's your horse, right? Tail, ears. But then also this is a shape. Then only one horse can fit, and then only one horse can fit. And the volume will be different. You can make it very fat, right? The material will be the same. So it's the same 2,400s. And also you can mess up. You can like start building it and accidentally did not finish it because you're out of material. Well, that's dumb. Don't do that. And then, unless you want to have a gate maybe. And then the other one is not very smart when you completed it too early and now you have leftover. And Uncle Jim gets mad because you're wasting material. So there's so many options. Your job is to know calculus, and that's actually how it works, to optimize those ideas. So there are lots of different cases, and I will show you at least 2 cases to compare. Can you figure out 2,400 for this example? What sides do I have for this awkward example when it only fits one horse at a time? What sides dimensions there will be if total is 2,400? I have it in my notes. No? 1,000, for example. It's a random example. Okay, if it's 1,000 and 1,000, what's the sides are, the left and right? 2 and 2, exactly, thank you. So we are talking about area, and then you will be doing volumes too. And then in calculus 3, we're going to do hypervolumes. So area is, what's the formula of the area of rectangle? Length times width, length. Length times width times length, correct. So I will have 1,000 times 200. Did not fit. That is 2 and all the zeros together. 1, 2, 3, 4, 5. 5 zeros. But can you figure out another example? For example, for this standing one. Any other dimensions? In my notes, I have like 500, for example. So if the width is 500, then what is the length? Out of 2,400? 700, exactly. 700. So it's still a fence. It even closed nicely. And the horses can fit nicely. Look at that. So let's calculate area. Area will be 7 times 5, 35, and all the zeros together. That is not the same number. 4 zeros versus 5 zeros. That's already a lot, huge difference. 20,000, 200, yes, 200,000 versus 350. So it's not, yeah, like this. That's not the same thing. So you're already messing up by losing area with some shapes and gaining it back with another one. So what's the best shape then? You know, and that's what we're gonna find out. Does that make sense? Isn't it cool that it depends on the shape? How cool is that?
Isn't it always the square?
We'll see. Good guess. There's a guess here that maybe it's always the square. And it sounds smart. Lots of things that we use are squares. But like even your notebook is not a square. But don't you want to optimize the area, maximize the area? So again, let me repeat. We are maximizing the area. Don't you want to maximize the area for your writing? And it's not a square. So let's see that why it is not a square. Why your phone is not a square? Isn't it the best screen to be the maximum area? So all of those are solution. All of those are decent or good questions for optimization problem. And I will put a contest in the forum for you to find more optimization problems. I will list some of my favorite, and then you figure out more. Step 1. I will give you steps. I think I have them written. But guidance. But again, it's a pretty creative process. But it always starts with reading the problem and drawing the picture. The picture helps a lot. If you can, do it. So picture goes first. Here's my rectangle. I will not make it a square to make it like general rectangle. I only know that they want me to have a rectangle, and I need to write down that area is unknown. We want to have maximum area. Let's call things lengths and widths. Lengths and widths, L and W. You don't have to. You can do X and Y. Doesn't matter. And I do actually X and Y often. So we have, that's all we have. That's the picture, very not informative, to be honest. Step 2, list given things. List given important info. So too much English, but that's the core point of optimizational problems. There's lots of wording involved. With the given fencing materials, I see a number as a foreigner, you know, as an ESL person, English as a second language. I see a number, I want to write it down. It means something. 2400s, what is that? Given 2400 feet. Oh, why did you say perimeter? What is that? How do you know?
Because that's what the perimeter is.
That's what the perimeter is. So
It's the total length of the wire in its, in all forms.
it all forms. So correct. Interesting how differently you explain this. So 2400s, they say given fencing materials. If they tell me the fence will be a circle, that's not going to be a perimeter anymore. That's going to be circumference, a star. Sometimes we need a nice stage for like raves. Here's your star. That's going to be literally the size of the fence used for the star. But since it's a rectangle and it's a fencing material, this is how it's built. This is how I imagine it. You put a pole here, and then you just go and go and go. Choose when to turn. Choose. Now you don't have to choose because you already know when to turn. And then complete. So that's the one piece of fencing, right? That means all of this is 2400. How do you call this mathematically? Perimeter. So even knowing this terminology means you have education. You have mathematical education. So that's how cool is that? And vice versa, if someone told you perimeter is 2400, your education tells you what it is for defense. And now let's write down things that we also have. We chose L to be lengths. Let's put units to be professional. W will be widths, because it's actually not obvious. What if L is what? Any like electricity? Because electricity. No, it did not work. What if W is gravitational forces? Okay, so you need to explain to people what it is. And finally, A is the area. And area is L times W. I was supposed to ask you this question, but I truly believe you understand this. A is the area equals to what? We don't know the number, but at least we know it's height times width, length times width, whatever you call it. And that is objective function. That's the function we want to optimize. In this case, let me write it down, to maximize. Don't get distracted with beautiful pictures on the right. I will mention them later. To maximize. Maximize. What are the units of this objective function? Feet. Feet times feet gives you feet squared. And in general, it's area. Area has higher dimension than length and width. Second dimension, 2 dimensions. So here is the stuff we have. Very nice. Is it all we have? I don't see any more information. I only know that we're concerned about the area. And then I want to make area as big as possible with the given things I have in my hands, which is how much material I have. Good. We're going to change the color and I will write down the model. Step 2. That was already step 3, I think. Yes. Step 3. After the picture, after listing what we know, let's identify the model. The model might have 75 equations. That's what my friend in graduate school was working on, the interaction of one cell with another cell, 75 differential equations. That's still a model. So in this case, we're going to have only 2 for now, because it's calculus 1. Objective functions and constraints. Restrictions, if you remember. Objective function is A. A has an equation, L times W. If it's volume, you write down the volume equation. If it's surface area, you write down surface area, and so on, whatever you need. We're going to have cost function later. And then we have P. And P is 2400. But we need equation. Do we have equation for 2400 with L and W? 2L plus 2W. So you add them up. W, W, and L. That's the definition of the perimeter. So P, perimeter. Write down the word perimeter if you're afraid to forget about it. And it's going to be 2L plus 2W. And that is 24 hundredths. That is your model. You can put it in the box. I will not. And I will call equation 1 and equation 2. Just keep mentioning them. 4, you start solving it. Step 4. You have steps to solve the model, to give the answer of this optimization problem. So that's where the steps start. So I want to, let me just ask you first. I want to maximize A, area. What does it mean to maximize area? What mathematical tool solves this question? People at the back? Who's getting crazy again? There's 2 people on the left. It's always crazy. And also, you're usually black and white. It's very interesting. Black t-shirt and white t-shirt. It's like yin and yang. And one is always crazy, and another one is always peaceful. So it totally makes sense. Oh, it's hot. Yeah, just go to the door. So, how do we maximize area? What's the mathematical tool we know to do that? Should be the synonym. Wait, people at the back. Just say it together. 1, 2, 3. Let me try again. What is the tool we use mathematically to maximize or minimize things? 1, 2, 3. Everyone. Well, limit is not the correct answer, but it's kind of part of the definition of derivative. You just did the whole homework. They ask you find the maximum, minimum, local max, local min. You never thought that might be useful in applications, so now you do. What is the optimal size of your hand so you can hold a smartphone? There is an answer for that. That's maximum. And actually, for you to know, it's a very complicated concept. Our body grows hands symmetrically, but actually that's not simple at all from a biological point of view. It stops growing them at some point. Why the length of the hand is this length, and then that one is this length? It stops. At some point there's a switch and the body says, good enough, don't grow hands anymore. And also they are the same, sometimes they're not. And that's when people struggle a little bit, when one leg is shorter than another one and you have to have like special shoe, or else your organs will be tilted all the time. So there's an optimal solution to things. If you want to maximize or minimize something, you take derivative of that. Set it equal to 0, find critical points, blah, blah, blah. If it's on the closed interval, make a list. If it's not, figure it out differently. So I want to differentiate A. I want to find A prime. And it's going to be product rule, I understand that. But we have 2 variables, L and W. We kind of know how to work with that with related rate problems. They all related through feet in this case, lengths and feet, width and feet, and blah, blah, blah. Money sometimes if it's a cost problem. But it would be nice to have one variable, something like x squared plus 5x, right? I don't want to have L and W. So what I'm going to do, I'm going to put this equation in the box and solve for one of the variables and plug it into the first equation. And you can choose any. So step 1, I'll put it in blue. Step 1, use 2, and it's a very scientific way to call an equation, a number, and then refer to it. 2, solve for one of the variables of the vars variables. Vars are variables, even though it also means something different in coding in medicine. So don't mind ladybug, but choose any, doesn't matter. X and Y, usually you choose X. In L and W, now it's like not biased at all. So 2L plus 2W, that's equation number 2. Equation number 2 equals 2400. I would divide by 2 first of all, why even bother? L plus W equals 1200. And then you choose for one. I would ask you, which one do you want to choose? That's the correct teaching thing to do. L, well, yeah, in my notes I have W, so I'm going to solve for W. It's exactly what parents do. That's what I mentioned last time. Ask your opinion, and then they do their way. W, but as you can see, it's symmetrical, doesn't matter. Sometimes it's not symmetrical, then it makes sense not to do the hard one. 1200 minus L, to be consistent with my notes. And that's not E, that's L. You see that L is ugly, that's bad. This we don't have this letter in Russian or Ukrainian alphabet, so that's not my good letter to do. Check mark. Plug that B or 2. Okay, 1. Second step, plug into 1, which is objective function. To make it easier, A will be, A was L times W. Now it is L times W, but W is 1200 minus L. Boom, you have equation of one variable, which is easy to differentiate. You can do product rule or don't. I would distribute, and I recommend to distribute and create common denominator if needed. You will have problems with common denominator later, and that's a good suggestion to create a common denominator. Here you go. Let me move my thingy lower. So, if you want to follow guidance, we are halfway through. We are on the step 5, with the objective function expressed in terms of a single variable. Single, now it has a one variable. Find the interval of interest, find the max min. Interval of interest is a weird phrase. I will ask you in a second, what do you think it is? Put this in the box, this is important. Because we need to maximize this, maximum. What is the maximum? And also we're looking for global one. We want the biggest area, the biggest one. So you actually start the process. That's step 3. And now you know how to do it. What do you do to find maximum of the function 1200 L minus L squared? Derivative. Let me change the color again. Why not? A prime is 1200 minus 2L. Put this in the box. That's also important. That is the derivative of the area of the fence you're building. And it makes sense because we want to find how fast the area is changing. Why do we care about that? Because, you see when I showed you different areas, this area is small, actually bigger, better than this area. This area here is bigger than others, but the material used is the same. So it means area is changing. Changing means has speed, velocity. How fast does it change? Instantaneous rate of change. So I want to know how fast does it change. That's A prime. How fast does the area change? A prime fast. When does it reach maximum? When A prime is what? 0 or D and E. D and E will not be used for applicational problems because we're always in a domain. Not always. There will be things when X cannot be 0, but that makes sense. Why would we have 0 lengths and stuff like that? So let's solve it. We have 1200 minus 2L equals to 0. 1200 equals to L. L equals 600. Doo-doo. That's lengths, feet. We found one answer. Actually, we don't know yet. It's a potential answer, so it's a might be critical number or might not. So we need to check if it's in a domain, blah, blah, blah. And then we perform first derivative test, or we do global list, which I also can explain why. The hint for your exam, that usually is the answer. All the numbers you find, guess what? They are the correct numbers. Because applicational problems, especially the simple ones, when the area or the volume is unique, it has one maximum. Why would you have more maximums? Why would the area will have one maximum and another a maximum? So usually that's the one. L is not the maximum. L is a length that will provide the maximum. So it is a critical point because it's in the domain. I don't know. Is it though? Let me check. To check if it's in a domain, which function should I look at? Original A. That's why I put it in the box. 600. Does it make anything weird? No. It's a polynomial. It's fine. But I have to say something bothers me a little bit. A is from minus infinity to infinity, right? Why do you think it's not? Why? You can have negative area. Even 0 would be weird. So I will show you later the animation, how it changes. So that means L should not be too big. If L is too big, the square makes it even bigger and negative. And from the point of view of building things, civil engineers should totally like this idea. The length will be super, super long. Then whatever is left will be width. And then you have to go back. This is a bad fence. Can fit a ladybug, but not a horse. And also you waste lots of area. So it becomes like a rope rather than a fence with the area enclosed. Same with the width. At some point it becomes so thin that it's a line with 0 width. 0 width times any length gives you 0 area. So obviously L should be not 0. Let's put bigger or 0 in the domain, and that means 600 is fine. But also, so A shouldn't be negative, so L shouldn't be too big. And L has some kind of maximum on the domain. And that's also interesting to find. Are we going from 0 to infinity? To find that, can you guess how to find what's the maximum allowed L should be? Which one to 0? A. When does A, this guy, become 0, the original function? Solve for L and get the answer. To solve, so we are looking for domain. 4th step is domain. I cannot answer the question about critical point if I don't know the domain. Obviously, L and W and A have to be positive for 0. That's fine. But then what is the upper limit of L, W, and A? There should be upper limit so A doesn't go negative. From this equation, L should not be too big. Plug L to be 1,000,000, doesn't work. So like I mentioned before, it's a very good idea. Find when A is 0. I'm just going to write it down. It's going to be 12, I already forgot, by the way. 1200L minus L squared equals to 0. Solve this, it's a quadratic function. If you factor L out, one L is 0 and another one is 1200. So L should be less or equal than 1200. Bigger, so let me connect. Bigger than 0, less than 1200. And you can say L belongs, C with a tongue means belongs, 0 to 1200. That is your domain for L. Domain for L means domain for W, domain for both means domain for A, and so on. Different books in the United States and different professors do not agree if we should include outside points or not, the end points.
Yeah, because it's not a rectangle anymore, it's just...
So basically it's a question, is a rectangle with 0 length is a rectangle? And also the question, the 0 area is a still area. So there's a debate on that. You can put open parentheses, that most people agree on that, but then it's kind of harder to work with it if you want to do closed interval method. So now you can do closed interval method, which is global min max. You can make a list, plug all those points in, you have 600, you have 0 and 1200, and guess what? 600 will be the answer. Or you can do first derivative test, and that's my favorite in this case, because sometimes finding domain is annoying and not even necessary. So for step 5, way 1, use list for global min max, and global min max, wait, remember, on the closed interval, on the closed interval. And that's the thing, if we don't include the endpoints, you cannot call the closed interval. So that's why I usually do call it closed interval. You make a list, you can do it at home. Make a list, plug 600 critical point, plug 0, 1200. Obviously those are not good numbers, they give you 0. And choose the answer. Way 2 is more creative. We're gonna use first derivative test. Even if I don't know the endpoints, I will draw a sine line for a prime, for the derivative. I will put 600, and I will plug points, test points, into the derivative to see its sign. Now, since we know the endpoints, we can put that we're going from 0 to 1200. So I would still choose points around it. For example, I can choose 500 and 700, or 1 and 1000, for example. Do you know what I expect to get if I'm looking for maximum? Do you know the signs I expect to get right now to get the maximum? Positive and negative. People like, yeah. Do you understand? Positive and negative means climbing up, climbing down. You go up, you go down, you get your max. Let's check. If I plug 1 into derivative is 1200 minus 2L. Plug 1 is positive. Plug something big, like something that times 2 will be bigger than 1200. 1000 becomes 2000, becomes negative. Perfect. Since it's the only critical point, the function will never change direction. So that is the only critical point we have. Not only it is local max, but because it's the only max, it's also a global max at the same time. And that is not the answer yet. But let me stop for a second. What do you think about all of this? Is it boring? Is it like, oh, it's not too bad? Is it like too much talking? That's how I feel sometimes. Too much talking. The math doesn't take as long as talking. So, and reading also. Who knew you will have to read so much stuff in the math class? In America, you do. They like applicational problems here, especially math for engineers. We have lots of hard applicational problems in calculus too. Right now, my students doing it online, and that came from the engineering department. Let's pump chocolate from the conical shaped container, and then we have a fountain for the chocolate. How much work it will take? Well, let's calculate work with the integral. Oh, don't forget it's also lifted by 5 feet, like all of this. So they hate it. But it comes from the engineering department. Solution or answer. Let's do answer. Answer. I'll put it in pink. L equals 600 feet. Yay! Is that a good answer? What do you think?
You gotta find the area.
That's not what we're asked to find. Go back and read carefully. You need to know what you're answering. So you are a construction builder. So my dad was building houses all his life, and he did a very good job. He has a high reputation around his community. His houses are around our neighborhood, and they're still amazing. So he gives the answer 600. What is that? What does it mean? They ask me the area. Why do I give you the links then? Okay, well, it means we need to find all of those things. And that's why I like that the equations are ready. A equals L times W. Okay, well, that means I need W. And in general, it's nice to know the width. So I'm going to go down, scroll down. Oh, here it is. This equation, let's call it star for a chance. Equation star gives me width. So width is 1200 minus 600, which is 600 feet. Did not fit, but I wrote down feet. And then area is L times W, and it becomes, what's the answer? 600 times 600. Let me write down 600 times 600, which is 360000. Collect all the zeros. 360,000. That is the answer. Feet squared. Don't forget that. Feet squared. Doesn't write? Yes, good. Feet squared. That is, can you explain to me what we're answering? Some professors are very picky about the answer. Don't give me just 360,000. You're supposed to write some English. They told me, teach students to write English, Julia. And I keep forgetting doing that. What did we answer? What is A again? It's not a hard question. You need to go back and copy paste what the question was. Okay. The maximum area with the given restrictions is constraints, right? Restrictions. 360,000 feet squared. That's the maximum area. What do you think about that?
So what square?
Yeah, that's my question. Did you notice how odd is that? Wait, it's just like a square. 600 and 600 each side. Length and width becomes a square. Well, apparently a circle and a square, a sphere and a cube are optimal shapes. And that's why we see them everywhere. Because if there's no other restrictions, and if you want to feed as many horses or candies in the box from Amazon, or whatever you want to do, the optimal shape is a square.
So if we're given this question on a test and we don't need to show work, we can just do the square.
Do you think it will always be a square? That's my next question. If the square gives you the optimal shape, here's your fence. Why, for example, your stadium with American football is not a square? And also, okay, well, it has this running circular shape. Then why it's not a circle? Should be a circle then. Why it's like, do you know what I'm talking about? It's like, it's supposed to be a circle, this American field. It should be a circle, but then they like took it out and connected with this rectangle in the middle. Why?
Maximize the area.
What are you saying?
Does it maximize the area?
Well, we want to have maximum area for people to run. Also, it's expensive to build a stadium. So why then it's not a beautiful circle or square? Anyone? What do you think? Be creative, yeah.
So they aren't turning constantly, because that's annoying to do when you're running.
Interesting. Not turning constantly because that's hard to do when you are running. That's a pretty cool idea. More?
It makes doing an event like the 100-meter dash a lot more difficult.
What is dash? 100 dash?
Sprinting.
Sprinting. Better for why it is better for sprinting though?
Because it's nice to just have a straight line, so you can just focus on just running
Oh,
on that straight line.
you run straight versus then you fall if you do. Yeah, sprinting.
It's also easy to tell who wins.
You went sprinting, you go straight line. More?
A lot of the time they're multi-use stadiums, so like the center will be a rectangular field, but they need the circular bits on the end for the running around.
For the running around. They're also good ideas. How about the audience? Is this the maximum audience to put around the circle or like this? That also matters. Who gives money to all those events? How does ASU make money? Every time all those people come to watch our football games. Yay! And to maximize that, they definitely increase the lengths to put more seats. That's like from practical point of view of people. Running, sports, all of this matters. Football and soccer. Soccer is the actual football. You know it, right? For you to know. So that means some other constraints popped out into the picture. That those other constraints changed the solution. Same thing about windows. I was always curious about windows. And that's where I'm going to show you some applications. If we want to maximize the area, so the area of the sunlight goes to the house, why our windows are not squares? Well, in old houses, they used to be. In circles, in submarine, it is a circle. Why they're not? Sometimes you want the house to go taller. Then they make taller windows versus, so like those windows over there, they're tall, not wide. They're not squares. Imagine having like weird squares everywhere. So that means some restrictions are there. And an engineers and physicists should also consider why this circle is used for submarines. There's another thing also matters there.
Pressure.
The pressure. Did you all guess about that? That's what I also thought right away. The pressure matters so it doesn't break, and then the circle maintains the pressure really well. Same with the 3D. Eyeball is one of my favorite ideas, is a beautiful sphere. Sometimes it's not, but biology knows to use optimal shapes if it needs to have optimal stuff on it. So the pressure of the eye matters, and that's why sometimes it's not a sphere, just like I found out last week. Apparently I need glasses. Apparently because the shape of my eye is a little bit squished. Astigmatism, right? That's what you call it. Yeah, whatever. So I did not know that. First generation in a college in my family got glasses earlier than my parents. So the sphere should be the perfect one when the light comes in, distributes, and you see the picture. So isn't it cool that nature knows it? How about the cells in your body? The cells in your body, circles are the center of the cell, right? But then they are kind of have elliptic shape because they move. Some cells move and the way they reproduce. That's also an optimal shape. And then another cool example is hemisphere. Hemisphere is a very nice idea. So I like ladybugs. Also, it's a very nice name in English, ladybug. We call it a bug of God. So like God sends you the bug, that's a ladybug. Somehow we truly believe that it's a good luck. And that's why maybe you saw in different movies that it's a sign of good luck. So it's a hemisphere. Isn't cool that it's a bug with a hemisphere on top of it? You should know also that there is idea of a smart city. Have you ever heard the terminology smart city? What if we can build a city from scratch? You can actually make it smart. You know, like there's so many big cities with a cemetery downtown. Super weird. Like my city has it because it's not used to be downtown. The town used to have like 500 people there. That was outside of the town. Now it's 1 million people and end up to be in the middle of the town, and then people debating to relocate that or not. So more often it stays there. Well, what if you can do it from scratch? Then, you know what? The hospital will not be close to the school for like obvious reasons. And that's what I was modeling at some point. How far the epidemiology hospital should be from not epidemiology hospital. So people with broken leg don't interact with the people with Ebola, for example. But usually they cannot do that. So at least have a different entrance. And we were modeling that. So they don't even interact. How far the hospital should not be too far from the schools, for obvious reasons too. So it's like very cool how you can actually model. And of course, Costco should be in the center. That's everything surrounds Costco for big families and everything. So it's called smart cities. And also, even if it's not a smart city, your GPS tells you the optimal way to go from one place to another place. Because actually, if you check how Google calculates the distances, it uses lots of linear equations really, really fast. I also did a project on that. It minimizes the distance based on the restrictions, traffic on the University Drive, how many lights there are, should you go to highway or not. So it does a very quick minimization problem. Finally, if you're into biology, I'll tell you about these things. I like that a lot. Trees figure out the optimal shapes of leaves for different scenarios. So if there's no wind, then we have apple trees. They have this very optimal shape to collect sun from the air, right? So they're very clever about it. But palm trees are made out of a specific shape that they can bend and not break, because there's often lots of wind in Florida and where the palm trees usually are. And then the cool example of willow tree, they always shake a little bit because they have long shapes of the leaf. Those leaves, a biological optimization problem. The trees with those leaves survived the competition. You do understand, right? That everything you see in front of it survived the competition. Natural selection. The trees with worse leaves died and did not reproduce earlier. Same with a cool example of Grand Canyon. If you go to Grand Canyon this weekend, you might see trees that are spiraling around on the edge of Grand Canyon and any other canyons, because other trees collapsed and died before reproducing. And naturally, the more it spins, the more wind would not break the tree, it will go around. Because of what? Aerodynamics. If you're going to be building planes, aerospace engineers, you know the words aerodynamics. That's how the planes are working. This side is not a big circle because we don't want the wind to hit us and we fly away. We want the wind to go through. That's how the leaves are also done in some trees with the windy territories. All of those optimization problems, and you will be doing them all at some point, including business problems. What's the maximum profit, minimum cost functions? What's the probability of the earthquake? What's the maximum probability and minimum probability? When you buy a new car, Toyota car, they tell you, we have we can give you insurance for 4 or 5 years. We know the car will not break. How do they know? Because there's an interval of probability of the Toyota car being reliable, and if you break it in 2 years, you are in as much as small probability that they will give you a new car. But they do know it's not going to happen. That's your minimum and maximum interval of insurance, for example, and so on. So I will make a post in the forum, and you can put your interesting ideas of the optimization problems to play with it. Do your homework. I made lots of videos on many of your homeworks. So I solved lots of them already. And if you cannot solve it and you're stuck, post the questions in the forum. And if that doesn't help, you know what you should do? Google. Those problems are very classical problems, so you will find solutions. Thank you. Have a great long weekend. I will see you on Monday. I'll go to office hours though. Look at that, the beautiful leaves. What's your favorite leaf shape? I like this guy. Oh, the heart is nice. What's your favorite leaf shape? So cool to see so many shapes. Which one? Where is it? Oh, this. Oh, yeah. I like the heart. Like, why did you decide to have a heart suddenly, right? But also, what the heck is that? So cool, right? I like to play with those. And look at this little crown. That's also pretty cool. Viburnum. How do you say it? Viburnum? Viburnum. How do you say that? There's some words I never heard before. Okay, let me stop talking. Just a second. And good.